Okay, in this lecture we'll discuss normalizations of data for accurate and correct trainings for big data sets, and we'll be designing a singly reinforced concrete beams based on artificial neural networks. And the beam section is such that we have a beam width, beam depth, and also the concrete compressive strain is assumed as 0.03 for design, and we have here strengths from levers, and we have neutral axis, and also we have a concrete equivalent concrete block based on witness rectangular concrete block, and all these inputs and outputs are generated based on any good software, any structural software can be used to generate output parameters for given input parameters. As you see over here, we generate 4 output parameters, which is a nominal strength of moment here, lever strain, and C over D and B over D ratio from given BD, low S, F prime C, and Fs. The low S is a steel ratio, which is calculated dividing the steel area by the sectional area. As you see over there, is steel ratio. How much you use your steel in the beam section for resisting loads. And we have to my experience, we probably have to have a 10 to 50,000 big data, depending on your complexity of your beam. If you have a singly reinforced beam like that, maybe 10,000 data should be okay. But if you have a doubly reinforced, you may need another 20, 30 more. If you have a pre-stressed beam, say, you may need a lot more than 50,000 big data. So you have to repeat generating all these big data sets based on a software. Okay. So here, one thing we can notice here, we notice that the magnitude of B and D is greater than those calculated for strands over here. If you see here, B and D is magnitude of hundreds of thousands, maybe 2,300 can be found here, whereas your strain is pretty small, 0.0026. So these two numbers shows big differences. So therefore, these numbers are not appropriate as a big data to be used at the same time. In other words, we have to have some normalized values, normalized ranges to make these numbers are compatible with each other when we formulate error function. Something like you see over here. Here we have gone through a normalization process, which I'll be explaining in a second, and you will see all the data, 10 data displays a magnitude similar to others. See, this data is normalized between -1 and 1. All the variables, all the parameters were normalized between -1 and 1, and they are very comparable. So that it's easy for us to formulate error function, cost function, to be able to minimize them reasonably. Selected structural data sets are appropriately normalized accordingly, thus resulting in well-defined cost functions shown in right here. Well-trained neural networks correlate network outputs with targets closely when you have this type of error functions, which is well distributed and well defined. However, input data sets and targets shown in here and also shown in here are not appropriately normalized right now. So we have a distorted cost functions. as you see here, I mean by distorted is that you're having a very small intervals between the error functions, whereas you have a wider distributions of error function in the other directions, which makes your cost function or error function distort, so that it hinders the convergence of the gradient descent and fails to prevent cost function gradient from overshooting or from being kept at a local minima. We're gonna learn how to use a gradient descent. Gradient descent. Listen to find the right path that the error function converges to its minimum value right there. And maybe if you start from here, this looks like a very nice path. So gradient descent tells you which way you go to minimize error functions by finding a very good neural networks which is leading to very good weights, very good bias. And we learn the role of weights. The weight is nothing more than a neural links between layers based on linear relationships. So that this really depends on your data quality. If you're not normalized, you're going to have a very difficult situation where you have a distorted error function, and it's very steep that your gradient descent is going down, which may cause as I said, a overshooting or from being kept in a local minimum. If this is really big, then it's going to go and overshooting. So we need to prevent those things from happening by having a very nicely spaced or very nicely normalized big data sets. This diagram shows that well-defined cost function based on appropriate normalization, whereas here we have a distorted cost function based on inappropriate normalizations, resulting in weak convergence of gradient descent. By gradient descent, we're going to find out the best path to go down to minimized error or minimized cost functions, and it's going to be very difficult if you have a distorted cost functions, because you can have a oscillation between cost functions, or you can have a exploding between cost functions. We need to have a well-defined cost function based on appropriate normalizations, resulting in good convergence of gradient distance. As you see over here, if you have very nice cost functions, and the gradient descent will tell you which way to go to find the minimum cost functions or minimum error functions, as you see over there. So good training, it gets you good trainings also, which is leading to accurate weights and bias. And again, the weights is nothing more than a linear neural links between neurons, between layers. So you need to have very nice weights and bias to get a well accurate ANNs to predict output from input parameters. In these diagrams, you have a one variable, so that you have a very simple cost functions, but things are different when you have multiple variables, as you see over here. This is one example to have a couple of multiple variants. You have a multiple kind of mountains over there where you have a big errors, and the big errors is probably calculated at the end of first epoch by the feed-forward network calculation and back propagations. So you are having a error function calculated, obtained at the end of first feed forward calculations, and then you calculate error functions or cost functions based on error functions. You go and perform a back propagations to revise your weights and bias for better prediction next epoch. So that from this couple of process, you're gonna find out again the way where you should go down to get a minimized error function or cost function based on gradient descent. This looks like a very nice cost functions that is based on appropriately normalized. Let's say you have a kind of contour here. Let's say how we're not explain from contours. So we have contours here. Or from the lowest point here. This is lowest point, which is a very small error. So you're going to contour this way in order to be consistent this way here. So if you see from downwards and you have a very big error functions over there, functional values over there, in this case you are having a distorted cost functions, and it is very hard to define gradient descent when you have a distorted error functions like that. And this is probably based on inappropriately normalized data. So that whether you have very good error functions and with very nice contours here and or not here, really influence on your training quality, so they will make it really difficult. You find a best bias and best weights based on neural link. See, an epoch refers to one entire calculating cycle on input data sets, as I explained. It also includes on error calculations, output versus targets. Output is the result of feed-forward calculations, and the target is a observed value. Observed value. This is real value. Okay. And subsequent adjustment to update weights and biases until networks are improved based on back propagations, as I said over there. The above steps are repeated for all training data sets based on back propagations, which is performed to adjust weights and bias, connecting multiple hidden layers as a neural link until a calculated output are correlated with the target or observed data sets. Okay, this is another example of a cost function with the multiple cost functions with the multiple variables here, and whatever how many cost function you have, it doesn't matter. You try to find the minimum location is here where your error function or cost function will minimize. This is the way you want to go down, and using a gradient descent, it's going to be okay. If you have very nice cost functions, it's going to be a little bit different if you have a distorted cost functions, and the cost functions is based on this backpropagation procedures. And I think I explained it once before, and I'm going to explain that again in detail with some examples. And we have a chain rule over there all the way here, so that we're going to calculate eventually the error, the rate of error with respect to weights at the end of backpropagations. And these backpropagations are not nicely done if you have a distorted cost function or error function. Weights and biases or feed-forward neural networks are adjusted by mapping inputs to targets through backpropagation, as you see in this loop right there. This is very important. This is one of the most common algorithms used in the training of ANNs, thus minimizing cost functions of training data sets between predictions and training targets. So this loop enhances a capability of a network to establish nonlinear relationships between inputs and outputs if a activation functions are implemented. Output predictions of previous layer is calculated at the end of feed-forward training, which is then succeeded by a computation of the gradient descent with respect to predictions. for application of chain rules as referred to a back propagation shown right here. So that your error functions here, your loss functions right there, and the derivatives of loss function is calculated. That is called a gradient descent, and that is also used with chain rule to calculate the rate of error with respect to weights at the end of backpropagation procedures, and see if you revise or update your weights and biases a little further. You have singly reinforced, maybe 10,000 epoch. If you have doubly reinforced concrete beam, you gotta go 20,000-30,000. Maybe you have PT beams, you may go further, like 50,000. So this very lengthy process, the back propagation and the very lengthy process to train your neural networks, and an entire process is depending on a good loss function. We call the loss function, cost function, error function, all the it refers to similar meanings there, and all these functions is also depending on a very nicely normalized data.